What we did last time was cover the first chapter, and I went over the first project. Let me just get oriented here. Let's see how good we got some people online. That's good. All right, so last time I talked about what this book calls Before You Begin, which is assembly language. And the authors of this book assume you've seen assembly language before. I don't. Even if you haven't seen it, you can learn some of it here, enough to get by, although if you actually had an assembly language course, it makes it easier. Anyway, and I showed you this product called Heasman that simulates the x86 assembler and makes it possible to practice in a fairly easy way. And now we're going to get a lot more into the detailed binary stuff today. So which is the real meat of this class. So let me get it right here. 127, chapter 2, life is good. Okay. All right. So we're up to chapter 2, which is stack overflows. This is the venerable attack that caused this entire field to appear. And this is we're following history in this case, which is something that's not always a good thing in science, but it is good in this case because this science is very new, and following the history that got us here is currently the best way to do it. So we'll talk about how buffers work in C. This vulnerability, and indeed almost all the vulnerabilities you are going to exploit in this class, are caused entirely by this language called C. C is a very strange language. C was designed to write Unix, and Unix was designed to unify mainframes. I was just talking to someone about this recently. Back in the 60s and 70s, I was in the game somewhat back then, you would buy a mainframe computer for $1 million from somebody like IBM. They would then give you a rack of about 10 phone books full of manuals, and you would now have to learn IBM mainframe language. And if you bought a VAX, you had to learn VAX mainframe language, which was totally different. You bought the thing, and it had a special language that ran only on that hardware. And this was, of course, for the birds. And so they invented Unix to unify the servers. And in order so every server would run the same operating system, and all you had to do was write a Unix compiler for each hardware. And you needed the language to do that in, so they wrote the language C to write that compiler. Now, C was designed to be mathematically precise, and the point of C was to be a little easier than writing machine code. But the people that wrote it, it's a very old language, and it was very closely tied to the hardware. So when you write in C, you are manipulating the bits in the computer just the way the processor does. And they just assumed that you understand exactly how the processor uses those bits. Later languages like Python and Java create a sort of fantasy world with these variables and data types, and you live entirely in the fantasy world, like a person driving an automatic car. You step on the gas and it goes. You don't even know how many gears you have. You never change gears. You don't have to pump the brake. It automatically does that for you. They live only in an abstract world of high-level concepts the way end users do. End users just open the browser, see a picture, click a button, and email goes. They don't even know what cables are doing, what the packets are, what the addresses are. They don't need to know. They live up at a high level. And that's the way later languages are. But C is not that way. When you write C code, it maps very closely to assembly. And that means you can make awful mistakes, and it does not protect you from them because it was never intended to make it possible for anybody to operate a computer without completely understanding how the computer works. In fact, it makes the opposite assumption. It assumes that you understand exactly what every command does at the binary level. And of course, that is not true of most programmers. But in the early days when it was developed, it was true. So we have this bizarre situation of people using a language that is intended for people that are experts at the binary level when they are not. So they do things that look reasonable and they're incredibly dangerous. And that's what leads to all these vulnerabilities. So we'll talk about buffers in C and then show a variety of flaws. First thing is information disclosure. Then we'll use GNU to look inside the binary, see a segment fault and the stack, and do some stack buffer overflows. Yeah.
Is C still used to code most operating systems?
Yes.
Or are they using something that is more fault-tolerant?
No, it's a very good question. Is C used to code operating systems or something more fault-tolerant, and they use C. And for high-performance software like Microsoft Office, they use C and C++. And the reason they do is because you need the speed. There are two huge advantages of C. One is when you write your code correctly, it can be very efficient, especially if you really understand the hardware. And the second advantage is if you compile the code and deliver only the compiled code without the source code, it is very difficult to read. And that protects intellectual property. Like if you buy Microsoft Word, what they give you does not mean you can easily copy it and make your own version. Whereas if they gave you source code in some high-level language, it would be pretty easy to do that. So but the main advantage is it's much faster. And if you have a really skilled programmer, they can make a much faster program that's under better control. But less skilled programmers fall in the pits. And so what has happened is, as these security problems became more and more disastrous, Microsoft improved C. Microsoft developed special C libraries that remove the most dangerous functions, change some parameter settings, and add some more control features to stop like the top 10 attacks. And so that is the direction things are going. And this, I must say, Jan Kaminsky is one of the luminaries of this field, one of the top 3 most important people. And he said for years that you're not going to fix computer security by getting developers to understand security. You're going to fix it by designing development environments that add the security in. Because, and I understand his argument, it sounds pretty convincing to me. A developer has got a job which is really hard, which is figuring out how to make it look good on the screen, figuring out all the cases, meeting the customer demands, and asking them to understand a complicated world of security as well is not practical. What's better is to give them some environment like Visual Studio and design it so it automatically blocks the obvious attacks. Yeah, but even better, just automatically fixes it. That's what Microsoft eventually did. Microsoft was, of course, I think, the largest one affected. All the Microsoft Windows versions were extremely vulnerable, and there were all these attacks. And their solution was to modify C so that when they used C, it wasn't quite as dangerous. Yeah?
Isn't the opposite also true? If you make the language too abstract, the programmers, if they do have the knowledge, won't be able to see like, oh, I'm just going to create an exploit because, you know, the API, you know, has a bug. You know.
There are flaws at every level. If you take a higher level language like Java, then the programmers can't see the binary, and so they would regard the binary exploits as someone else's job, but now they have a different level of logic flaws, where one module might make assumptions about what another module is doing. I mean, there are errors at every level. But you're certainly right, and of course, the old school C and hardware and assembly language programmers are very unwilling to use these high-level languages. They say, I'm not going to do that. I want to know what my code is doing. And, you know, just like real car experts will only drive a manual car. They'll even build their own car. They say, look, I'm not going to have some idiot putting a bunch of sloppy junk between me and the car. I know what I want. You know, so these different philosophies are all out there. So this is the first vulnerability. This was known by the black hats and exploited for a while. And Aleph 1 was the first person who wrote a really good tutorial for this. And this created a modern generation of hackers, which we're now joining with this class, is people who understand how memory can be exploited. And this helps, you do have to understand what's really happening in the machine. You wrote this thing in 1996. This started the modern world of buffer overflows. It was a clear enough tutorial that you could understand it. And essentially everything I'm teaching you is just a rewriting of this. So a buffer is how you store a group of data in C. So you just have a series of bytes in order. And so let's make some exploits. Let me just take a look at one of these. I've got Kali here, and this is why I said you must have a 32-bit version of Kali. All this stuff happens in 64-bit versions, but it looks a little different, and that's frustrating for people, so you should start with a 32-bit version. Now, I've got 2018.1, the 32-bit version, which is one minor version back. I'm pretty sure everything will still work if you get the latest version, 2018.2. Now, you can actually copy and paste code into this window if you have VM tools running, but VM tools runs very badly on Kali. And every time you get it working, they break it in the next version until I've just given up, because this whole idea of virtualization on a desktop is stupid, and I'm trying to quit using it. This has no value in the industry. If you try to get a job and you say, I know how to run VMware Workstation, they'll say, so what? Nobody uses it. It's only a training tool. What we should be using is Amazon Cloud. And I'm trying to rewrite all my projects where you just put all your machines on the cloud. And I haven't got there yet, but I'm hoping the next semester I'll be there. I've already begun doing that for some of my classes. So you ought to get used to controlling a cloud machine. So just if it was in the cloud on Amazon, you wouldn't have any access to this desktop at all. And that's the way we should all get used to living. So in order to do that, you install SSH. And you'll find the instructions in the projects here. And so you control your machine with SSH. So let me get rid of this one and go back to this one. Good, I'm connected. All right, so I'm connected over SSH to my machine. All right, and I've got some code samples here. So let me go look at my slides. This one, yeah, this one is chapter 2A. So let me just bring it up here, ch2a.c, all right, and make it big. Get rid of the colors. All right.
Oh, colors.
Yeah, I think the colors are bad when projecting and screenshots. The colors might help you on your machine, but when projecting and stuff, I like it nice and black so you can see it. Okay, so here's a very simple C program. And this, by the way, is why people ask me, do I need to take a coding class first? And the answer is not really, because we're not doing anything resembling real coding, where you write pages of stuff and get the bugs out of it. We're doing little bits of code to understand what's wrong with it. We're zeroing on a little spots where the security hole is, and we don't care about all the other stuff. So here I have a program. Everything has to be a defined routine or function or subfunction. The main function is where C starts, so you have to have main, and that's all I have. I define an integer with 5 numbers in it, 1, 2, 3, 4, 5. So that would be fine, and if this were a high-level language like Python, it would make 5 boxes and put 5 numbers in it, and if I then tried to use one beyond the end, it wouldn't let me do it. Now here's another irritating thing about C. Everything starts counting at 0. I don't know why. There was once in 1974 this ancient language called BASIC that didn't do that. But ever since then, we've all learned that the first number is 0. I don't know if you take a kid and ask how many candies do you have 0. Unless I give you one, now you have 1. I don't know. Anyway, so this is array 0, 1, 2, 3, and 4. There is no array 5. But I could try to print array 5. Now, if this was Python or Java, it would just say there is no array 5, get lost. But C does not do that because C doesn't pay attention, doesn't know what it's doing. So when you make an array with 5 elements, C finds some memory, makes a pointer to the first byte, and then reserves 5 bytes starting there and puts in these values. And you can use this number, array 5. It will point off the end of that list and you can totally use it. You can read it and write to it because that RAM location exists, and C does not bother to guess what you're doing. And notice that you only expected to use 5 of them. It just says, you're the programmer, I'll just do whatever you say. If I can turn this one line into a valid line of assembly, I will just do it. Now, I saw something flicker by. I wonder if I have a chat message. It has to do with arrays, multiplies the index by number of bytes and adds it to the first element. That's right. That's right. So the array 5 just means start at array and then jump forward by the right number of bytes to hit the 6th element. Now, I have another issue. My power is not giving any power. Let me solve that, or my lecture will come to a screeching halt. Apparently this doesn't work, so I have to move it to the part of over there. Okay. It's a good day if that's the worst problem I have. So, all right. There we are. Aha, power, life is good. All right, so, all right, I'll compile that thing. I've already compiled it. Let me just mention, when you compile it, I use a couple of compiler switches, and this is why the version of Kali matters. In the old days, you would just GCC that file to compile it, but if you do that now, you get complicated modern versions of position-independent code, which is more complicated than what I'm showing. So I use the NoPy and the static options here, which cause it to compile this in the old-fashioned way to make a normal, simple executable, instead of the modern one, which is confusing. And I also have the -G switch, which means if you guys are trying to use those machines, it's CNIT, CNIT. Yeah. Anyway, yes, that's another example of how they do things around here. Anyway, they couldn't figure out how to install them to automatically log in. Anyway, so there's CNIT. Anyway, so -G means include symbols, so we can use source code, and we're going to use that. So when you compile this thing, you can now run it, ch2a, and when you do, it prints this big, strange number. And that is weird. I have now found the value of some location in RAM that is not one of the ones I reserved for my use. I took the first 5 values and I put in 1, 2, 3, 4, 5, and now I have read a value which was not reserved for my use. This is an information disclosure vulnerability. I can read data that I'm apparently not supposed to be reading. And that is the first simple vulnerability, information disclosure, a fairly common Friday bug where you get to see something you shouldn't be able to see. So let's take a look at this in the debugger and try to understand why that happened. There are a lot of debuggers for many different languages, but I highly recommend just using the oldest, simplest debugger, GNU debugger. There are a bunch of ways, people that try to make GNU debugger easier, and in my opinion, it's a total waste of time. Now, if you Google the GNU debugger, you will just want to cry, like Photoshop, because there's no tutorial that's less than 50 pages, and they're like 300 commands, and you just want to die. But you really only need to know 8 commands. That's all we're going to use. So I recommend ignoring the online tutorials. That's why I wrote this stuff, to try to make it easier. So GNU debugger, and I use the quiet mode just so it doesn't print a bunch of junk on the screen, and then name my program, 2A. Okay, that loads it into the debugging environment where you can run the program, and the only difference is it's running under the control of a debugger, so you can stop it and you can examine the variables as they go by. Otherwise, it's like running it, pretty much like running it in the normal operating system, although there are some irritating differences that we will come across later. So now I can do a list. Look, just list, and it will show me the source code. Because I compiled my program at the -G switch, I can work at the C source code level, which is not normal. This, by the way, is what real developers do. If you're writing your own software, you compile it with symbols, and you debug it in this way on your own source code, and you don't really have to know assembly. So for beginning projects where we're writing our own code, we can do it this way, the way real developers are, but when analyzing malware, you don't have this luxury, and you have to learn how to do it at the assembly language level. And we'll get there, but we're starting here. So here's my program. So I notice here, it prints out value number 6. So I would like to know what happened at this point. So before I print it out, I'm going to break so it stops. This is line 6, so I'm going to put a break at line 6. Now I'm just going to run, which is just what you think it is. It runs, but instead of finishing and closing, it stops here, because now that I've stopped in the middle, I can examine memory. And I can examine those values. It's X. I just don't use this high-level stuff much. X8X ampersand array. Okay, X8X ampersand array. That will print 8 items of the array. And I should be able to make it fit on my screen eventually. All right, so this is the values. They are 32-bit words. We talked about this before. It's a 32-bit processor. It uses bytes 4 at a time. So the first one is 1, 2, 3, 4, 5, because that's what I put here. I put them in there, 1, 2, 3, 4, 5. And here is the one word past the end of the array. It is this large number, 08049660, and that's the number it prints out. It reads this value, which I have no business knowing. That value will come back to be important to us later. But anyway, that's what's going on. You have reserved 5 spaces, written in data, and then read something off the end that is some other number being used for a different purpose by the computer, and is really none of your business. And C does not stop you from reading it, which is the ultimate cause of this information disclosure vulnerability. So now we have done these 4 commands. This is half of all the GDB you need to learn. Yeah. You can. In the debugger, you can change it. And in C, you can change it if you write to it. And that's where we're going. Absolutely. So this is information disclosure where we read where we shouldn't be. And to do remote code execution, we have to write where we shouldn't write. And we're getting there. Exactly. So now you know how to list source code, run a program, put a breakpoint in a program, and examine things with X. That's half of everything you need to know about GDB for what we're doing here. So now let's go up to a denial of service exploit. So we're going to do just what he said. We're going to write past the end of an array. So here I have a program. Let me just bring it up live. This is, I'm going to quit the debugger, and I'm going to nano ch2b.c. Oh, and again, get rid of the colors and make it big. Whoops. Escape Y gets rid of the colors. That goes to the end, and that makes it big. All right. So all I did is the same thing. I define an array, and now, even though I defined it up to 5, I try to write to location 1,000 words off the end of the array, and I try to put a 1 there. So let's do that. If I run that program, which is ch2b, that's right, I get a segmentation fault. The computer detected that something was wrong about what I did and complained. So that's interesting. And if I want to know why, I think I'll just go on to the other one. Yeah, there's more information. So let's take a look at ch2c. Let's see. Okay. Oops, not nano. I'm missing a space. All right. So again, all right. So I just modified that program a little bit. So I have my array of 5. I also define an integer called I. Now I make a loop that's going to go from 1 to 1,000 by hundreds. And I'm just going to print into that location. I'm going to print, I'm going to set it equal to 1, and I'm going to print the address before I do that. So I'm going to try to write at the start of it an array 0 and print the address, and then put a 1 in there, then go 100 after, print the address, and put a 1 in there. Notice, by the way, this thing here, this is how C prints things. You print, then you have 2 values when you print. The first one is called the format string, which specifies how you want it printed. The second thing is the thing you want to print. So I'm going to print array sub I, but I want to print it as a hexadecimal number. That's %x. Now, there are a series of these format strings. %d is decimal numbers, and %s is strings, and so on. And this just seems like a harmless issue of appearance, but this is coming back to be really, really important around chapter 7. This can lead to complete machine takeover. Almost everything about C has giant holes in it. This is one. Anyway, but we'll come back to that. I just want to mention in passing, don't forget about this innocent looking thing called a format string. It's going to come back and turn out to be really important later. Yeah.
Why are you jumping back?
Because I just wanted to see it without having to scroll by too much. That's all. No particular reason. So let's run this thing. CH2C. I got to spell it right though. All right. And what happens is you see it counting. Here's where that array starts, apparently, BFFFFC38, F638. That's a 32-bit hexadecimal number. Then it jumps ahead by hundreds, which is some not terribly obvious amount in hexadecimal. And then it goes up to C1000. And when it tries to write numbers starting with, to addresses starting with C, I get a segmentation fault. So I have got an idea where the limit is. Apparently, the limit is around where it went from B to C. Something I went off the end of something that was so drastic that the computer realized I'd gone out way beyond my bounds. A more high-level language, like Python, would have figured out I went past my bounds when I went past the first 5, which is all I reserved, but C didn't care until I got down to like 600 or 700 down there. All right, so we might want to wonder why did it stop at that value? And you can see it by looking at the memory map. So let's put it into debugger, gdb ch2c. And now I'll do list. Now you can't print the memory right now. You have to actually be running the program. So I'm going to list it, and I'm going to put a breakpoint someplace. It doesn't really matter. I guess I'll put a breakpoint in line 10. I just have to have the program running. And by the way, you can abbreviate commands. You can abbreviate them to any small size as long as they're unique. And you can finish them with the tab key if you want to spell them out. I get used to the 1-letter abbreviations, B for break and so on. But anyway, I'll break at line 10 and run the program. Okay, now it's loaded into memory properly, running, and paused. So now I can look at the memory map with info proc mappings. That's the memory map of my program. Every program has one of these, and this is going to be at the heart of everything we do in this course. You are going to mess with structures in memory. All these vulnerabilities are memory corruption exploits, where you do the wrong thing to the contents of memory and take over the machine. And this is the large-scale summary of how memory is used by this program. There are 2 things here. 804 is where most of the code is. There's more code up at 80D7. Those are both just named after my program. Then comes the heap, vbar, VDSO, and the stack. The stack is the thing we care about most right now, and later in this class we are going to do heap exploits. But the stack is the simplest area of memory to exploit, and that's where we're going to start. And the stack goes from BFFDF00 to C1000, and it's actually not very big. And there was a CTF problem I did a couple years ago where I was able to inject code on the stack, but I couldn't find it. And I tried and tried to find some way to find it. I finally said, you know, this is not a very big range. I just put in something big, and I tried all the values. There's only 21,000 of them. You can just try them all until you find where it is. That's brute forcing the answer, and that's often the answer. Anyway, so we're on the stack, and the end of the entire stack is at C1000. So the reason why it stopped and said segmentation fault is we were attempting to write beyond the memory that had been reserved for the use of this program. That's why the operating system said, no, you can't do that. Yeah. Oh, I do. All right, let's see. Might be something coming in on the chat. Thank you. Why is there no live C? Why live C doesn't map? Oh, that's a good question, and I don't know the answer. Someone else may know, but I do not know. A better developer than me might know. Yes, the library should be there and so on. When I loaded live C, there may be some way to see that. I think the debugger is not showing me the system libraries. That's a good point. Anyway, so that's what I wanted to show you there. That's why it crashed. So we have now made a denial of service exploit. By reading off the end, we had vulnerability, we had information disclosure where we could see something. By writing off the end, we could make the program crash by exceeding the allowed memory. So now let's try to improve our exploits down to something more fun, like executing code instead of just crashing the server. And for that, we have to be a little more careful about how we use it. So the point of the stack is it is designed for calling subroutines. That's why it has this memory structure. So you push things, it adds them to the top of the stack. ESP points to the top. Every time you push something, it makes ESP bigger. You move up higher on the stack to make room. And when you pop, you take things off the top. So when I'm in a subroutine, I have local variables here. And we're going to see more of that. So pop takes items off the stack and makes the stack smaller. Push makes the stack higher, and EBP points to the start of the current stack frame, which we're going to see. So yeah, go ahead.
Doesn't the stack need to be programmed in the higher?
What's that?
If the heap grows up, the stack grows down. The stack.
The stack goes up, and the heap goes down.
But it grows up to lower numbers.
I think
Oh, maybe
no,
not.
ESP gets bigger.
Higher number?
Yeah, I think so. We're going to see. We'll see in just a minute. That's the kind of thing a more computer sciencey guy would be absolutely right. We're going to see it live, and then we'll see. I forget you static mapped into the text segment. Oh, good point. And Amber Unix, you probably understand this better than me. A real developer, like especially an operating system developer, will understand these sections a little better than me, and I think this guy is one of them. Anyway, so
So I had a previous question.
yeah.
So in production systems, when you get that stack overflow,
Yeah.
and the server or the CPU crashes, do they automatically reboot, or do they just?
That's a very good question. I'm just repeating it for the mode attendees. She says, when you get an overflow and a dial service and the thing crashes, will it automatically restart? And that is up to the people that design the system, but usually, of course, they make it automatically restart because they want to serve up packets. And that's why there are, you can often develop exploits. In fact, about 3 years ago, Stanford actually wrote an AI that will do everything in this class automatically. It will find a process, fuzz it, develop the exploit, and perfect the exploit with no human in the loop. Because you will see this is a fairly mechanical process, but in order for that to happen, it has to be willing to just restart 300 times from crashing without complaining. And some processes will, like Cisco routers will totally do that. When you crash a Cisco router, it just restarts and keeps going. And because the normal use case of a Cisco router is people install it and nobody touches it for years. And you just want the packets to keep flowing, and you don't really care if some of them get lost. It's like your water pump or your electric meter. You just want it to keep going. You don't really care if it has some kind of problem. So they'll just cheerfully restart 100 times. Other things you would think after it restarts 10 times in a day, it will notify the administrator if something appears to be wrong. But that's up to you to set that up on your servers.
That's a good way of detecting if someone's trying to do it.
It is, absolutely. So when you're doing penetration tests, they usually try to avoid things that crash the server for that reason, obviously, because you're likely to get caught if you start crashing the server. But in practice, as we know, computers fail frequently, and you often do design it so the first 5 times it'll just restart without bothering you because that's just normal life.
When your server's crashing, you don't automatically assume that something.
Oh no, as we know, Windows updates, minor hardware problems.
It might be someone trying to test your system.
It could very well be an attack, but it could also just be things working as well as they ever work. So EBP is used to calculate addresses on the stack. If you want to refer to some value on the stack, and if it's right at the top, you can use push and pop. But if it's down lower, you have to calculate where it is. And you could, in principle, subtract from the ESP, but it's traditional to calculate from the EBP because that usually stays fixed as long as you're in the same subroutine, whereas ESP keeps changing. So you'll see in assembly language a lot of addresses like this, EBP plus 10, EBP plus 30, that sort of thing, pointing out to, that's 10 is hexadecimal, 16. That's referring to data on the stack, and all your local variables live on the stack like that. Now, the real reason the stack is there is for functions, and here's the point. The whole way all structured programs work is you're in a routine like main, then you call a subroutine like get input, it calls a subroutine like print. You have a routine, a subroutine, and a subroutine of a subroutine. So here's what happens when you call a subroutine. The calling program has to stop doing its instructions. You get to the one that says call a subroutine, and it has to not proceed to the next one, but go do the subroutine first. has to save its current state. Just like if you're working on something and the phone rings, you have to somehow save your place, go deal with the phone call, and then come back and try to remember where you left off. That's what goes on here. So it has to save its current state, transfer control to the function, then the function has to do whatever it's doing, and the function exits. Now it has to return to the calling routine and restore the state. And the point is, it had to store this state in memory, and we had an opportunity to alter that memory, so when it tries to pick up where it left off, we have fooled it into doing something different. That's how you take over the machine. It is the return from a subroutine that is the vulnerable step that gives you control of the machine. So inside the stack, after you call the function, there's your local variables, there's a saved EBP, and then there's a return value right at the end of the current stack frame, and then other variables. So we're going to see that. It'd be more easy to see live, actually. So that's the point here. So when you enter a function, you push before, in order to call a function, you push the arguments onto the stack, then you go to the function, and the function finds them on the stack and uses them. And when it returns, you come back to the saved EIP. So when the function starts, it executes a prologue, pushing its EBP onto the stack and creating a new stack frame. So it has its own temporary memory region for local variables. So it has to make, that's what's called a stack frame. It moves EBP up and then decrements ESP above that and creates a new region of memory to use. And when it's done, it puts them back where the calling routine expected them to be. So you're using another region of the stack. And this is why every layer of subroutine you go down uses up more and more of that stack segment. And at some point, there'll be a limit, and it'll crash because you're nested too deeply. But it's pretty far down on modern machines, and you're not likely to hit it. And so we'll see this stuff live. Here's a function with the 1 and 2 calling there, and you'll see this sort of thing. You're right, the stack does grow to low memory, according to this chart, and we're not, seem like I see it the other way. Let's do it live, and we will answer this question live. So here is CH2D. Let's take a look at this one. All right, so get out of this, and nano CH2D. All right, so here's this is about the most complicated function we're going to use today. Well, not necessarily, but it's pretty close. All right, now I have a main routine down here and a function. And the function has 2 arguments, 1 and 2. So I'm going to go to the main routine. I'm going to call the function. The function is just going to make that array and do nothing else and then come back. And then it's going to print return from the function. That's it. It doesn't accomplish anything, but it does set up memory and use a function so we can watch it happen. So let's GDB it. All right. And let me just check my notes to make sure I'm on track. Yes, we're going to list it and put a break. Okay. So list. Here's I want to put a breakpoint in. I think I'm going to list the whole thing. List 1, 12. That'll give me the whole thing. And I want to break at 10 and 2 because I want to break before I enter the function and then, not 2, but 6, inside the function before I return. So I want to see what the memory looks like before I enter the function and see what the memory looks like inside the function. So I'll break at 10 and then break at 6. Okay, now I run it. Now I've hit the first breakpoint at this line, function 1, 2. So I'm in main and I haven't done anything yet. Now I want to see what I've got. And I'm going to do info registers is all I need to do. Info registers. This shows me the registers in the processor, which are the same thing we saw last time in that simulator, Jasmine. EAX, EBX, and so on. The only things we really care about right now are the stack and the instruction pointer. This is the current stack frame going from ESP to EBP. That is the base of the current stack frame, and this is the top of the current stack frame, so there's only 8 bytes big in this case because the main routine doesn't have much data stored. Yeah. EBP. Extended base pointer and extended stack pointer. Used to be the base pointer and the stack pointer. And so that's how big the current stack frame is. It goes, and so it's only 8 bytes big. And here's the instruction pointer. The instruction pointer points to the assembly language instruction main plus 17, which will be the next line of code after the function. So these are the 3 things we care about. And you can see the stack goes from 610 to 618. And this is where we can answer that question that was coming up. The stack go to bigger or lower values. So main goes from 610 to 618. All right. And I can't remember in theory what the answer is, but we can find out in practice because all we have to do is continue And now do info registers again. Now we are in function. And now ESP and EBP are 5E0 and 600. So what people were saying was correct. Now we are in function. So the next stack frame is actually at lower addresses. The stack goes up to lower addresses. So it is 5E0 to 600. Okay, and each time you call subroutine, you put another stack frame on top, and the local variables go in there. So let's take a look at the stack here. We can do that with X20X ESP. It'll just show me memory starting at the stack pointer. Now notice EBP is 600. This process we're about to do is something you're going to get very good at. You have to do this all the time, which is find the current stack frame. The stack frame goes from 5E0 to 600. So I'm going to start printing, and you have to learn how to read this funny looking diagram. So there, 5E0 to the base at 600, it goes like this. There is 600. When the address says 600, what it means is the entire 32-bit word starting at location 600. So that is what it means when it points to 600. So this is the current stack frame. That is the data that is reserved for the purpose of this module, and the very next word is the return value. This number right here, 80488EB, is the address of the next instruction to be executed. And up here is the 1 and the 2 that came in as function values. So, all right, I think that's all I wanted to show you on this one. Let me just check my slides and see if I missed anything. There, examine the stack frame, there you go. All right, and we can see, by the way, remember I said this number right here is the instruction pointer, 8EB is the instruction pointer. If I disassemble, I can see that. So let's remember that number, 080488EB. 080488EB is right there. And this is what a function call looks like. You push the arguments, then you call the function. When you're done, you want to resume here. So when you call the function, it pushes that value onto the stack and then makes a new stack frame on top of it for the function to use. And when the function is done, it returns to this stored value. So on the stack is where you have an address copied that you can modify, which will be used for the instruction pointer later. And that's what we're going to do. All right. So we go back to my slides. All right, so that's what a function call looks like. All right, there's the prologue, by the way. I might as well mention it as we go by, although it's not exactly essential right now, but if you disassemble function rather. All right, then you can see when you enter function, it pushes the EBP value on the stack, and then it moves the EBP to ESP into EBP, and then subtracts 20 from ESP. What that is doing is storing the old extended base pointer, so I can restore it when it's time to return, and creating a new stack frame on top with enough room for local variables. And this is what the compiler does, is decide how much room you have to give it. So it reserved 20 in hexadecimal bytes here, and here it is storing those values in that array, 1, 2, 3, 4, 5. Which is 5 32-bit words requiring 20 bytes. But this is a little more because it's 20 in hexadecimal because there's some overhead. Yeah?
What about globals?
Globals are stored elsewhere, not in the stack. So I mean, globals are fine, but they're not easy to get out of overflow. In fact, they're often not writable. Yeah?
Why did the compiler put in no op?
This is, NOPs are going to be real important to us. The reason you have NOPs is to fill up 32-bit words, because some instructions are not allowed to start in the middle of a 32-bit word. The instructions are all different sizes. Like this one is only 1 byte, this one is 2 bytes, this one is 3 bytes. It takes a different number of bytes for each instruction. And some instructions must start on a nice, even 32-bit word, so you have to pad it with NOPs. And so that's why the NOP exists. Yeah? Yes, that's word align. Yeah, exactly. Good. Yeah.
I don't know if I'm out of context. It's 32 because this is an x86 and
Yes.
an 64 and an x80 and an x64.
Yes, if you use a 64-bit operating system, all these addresses will be twice as long.
And then if it has to be on a boundary, it would have to be a 64
Well, no, actually, I'm not sure about that boundary. There are different rules. You have to read the detailed assembly manuals to see what the boundary limits are. It is more complicated than that because each version includes a lot of instructions from the old version and a lot of rules from the old version. So in a perfectly logical world, that would be true, but in fact, it's just sort of a mess. In fact, when we get to 64-bit machines, you're going to find out they really rip you off. Large portions of them are really only 48 bits, you know. 64-bit is a marketing term, like 4G and 5G in the wireless world. It doesn't mean something as simple as it probably should.
But it is backward compatible.
In Windows, it is backward compatible, not in Linux.
Oh, thank you.
Not by default. Anyway, all right, so that's because Microsoft puts an enormous amount of work into being backward compatible in order to sell their operating system. Apple doesn't. If you have 2 versions back on the Apple, Mac says, get lost, we don't care about you, throw that thing away. And this frustrates a lot of people, and it's one of the many reasons why Macs are not common in companies. Apple only thinks about home users. They do not think about a company where you're going to have 10,000 of these machines for 20 years, and you have to maintain them and secure them and update them and do a quick query to find out what version of everything they're running. They are just not on board with that. And they drive the poor server administrators nuts when people start using Macs on your Windows domain. And all the tools you need to answer intelligent questions like how many machines are out there and what version are they running, there's no good way to answer that question. Anyway, so there's the saved return address. I showed you that number, and that's here. So let's make an overflow exploit. Now we're ready to exploit a real program. So this is a simple one, ch2e. Let me bring it up live. All right, so get out of here, nano ch2e. All right, so I have this function I call user input. It defines a 30-character buffer and uses getS, which reads from the keyboard to fill it, and then just prints out the answer. And then all main does is call user input and then return. That's the whole function. So the only thing different than the previous one is instead of just doing nothing in the subroutine, I'm taking input from the user. So let's run that one. Get out of here. If I just run it, ch2e, and I put in data like Sam, it prints Sam. So that's fine. But if I put in data like this, oops, I'm going to use capital A's, not control A's. All right. If I put in a lot of data, then I get a segmentation fault. So now I've got a denial of service exploit. I can crash the server. So now I'd like to know why that happened. So let's run it in debugger, gdb, in quiet mode, ch2e. Okay, and now I'm going to just run it. And I'm going to put in that long string. I'm going to copy and paste it. Okay, now it crashes. And when it crashes, it gives me some information here. Something contained 41, 41, 41, 41 that shouldn't have. And I can find out what that is by doing info registers. And I can see that EBP contains 41, 41, 41, 41, and EIP contains 41, 41, 41, 41. So I have now 41 is the hexadecimal code for an A. So some of those A's I typed in went into those registers. This means I control those registers. Now, you can take over the machine, usually with any degree of control, depending on how good you are at this game. But the easiest way to take over the machine is if you control EIP. Then you can just point to any instruction you want. So that's why this is where we all start. This is the simplest attack where you get direct control of EIP. Now, it's pretty much a piece of cake to take over the box. The only thing you might want to do is you might want to target that more precisely. And I forget whether I did that in the thing here. Yeah, let's just take a look at it. We're just going to take a look at it here in memory. So if I'm going to list, come on, list. Okay, hey, stop messing with me. Something appears to have crashed on me. Now that's working. What's going on here? Somehow my machine has lost its connection. All right, terminate. Let me try again. That's 172. All right, let's try IP address. So, all right. It's my Ethernet crashed. This is glorious VMware. My Ethernet has stopped Etherneting. It likes to do this nonsense. I'm going to reboot. This is one of the many irritating things about VMware on the desktop. While you just use a cloud machine, you'd be outsourcing this to Amazon. You'd just be yelling at them when it went offline instead of having to fix it yourself. Anyway, I'll reboot my machine, which forgot to stay on the network. This is very, very common, that these desktop virtualization products just randomly quit networking. And it's one of the many things that motivated me to start using them in different ways and get myself moving towards the cloud. So I could log in, and I think I'm going to have to, because I don't think I made SSH start automatically. Let me check. All right, root and tour. Now I'm going to open a terminal and make it bigger for people. Okay, so I do ifconfig. All right, a little bit smaller than that. All right. All right, so now I have no address. That's not good. DH client minus D ETH0. And it is failing to do DHCP. This is depressingly common. Activation of network connection failed. All right. This will happen to you. And I don't know if I mentioned it in this class, but when you do your hands-on project, they're just a smokescreen. What you're really learning is debugging. You will have all kinds of problems like this, and you will be forced to cope with them. And that's what they really pay us for on the job. Whatever you practiced in class is not really what you'll use. You're really having to constantly solve problems like this. So let's see if disabling and re-enabling the NIC works. It doesn't look like it does. Let's try ifconfig, ETH0 down, and then up, see if that does any good. And now let's see if I have an IP address yet. ifconfig, and I don't. Okay, the other thing is to go to other networking modes up here. I can go to bridge. I've done, this is all bugs in the various layers of software, and it's very common. So I've got an FE80, but that's no use. Let's take it down and up again and see if that does any good. Then I'm going to restart VMware, and if all else fails, I'll have to try a fresh virtual machine. Aha, okay, down and up finally worked on bridged. This is VMware Fusion failing. All versions of VMware have always been this buggy. They never seem to fix it. I've been using it for 10 years, and the networking is always like a loose broken cable that loses connection. You have to jiggle it around and pull it out and plug it in again. In fact, it's not, all right, I'll just switch to this address, 147, 144, 211, 246. Let's see if it will let me connect on that address. So it would be SSH root at 147, 144, 211, 246. And it won't because SSH is not running. I have to do service, start, SSH, SSHD. Oh, come on, open SSH. Fine. All right. It's probably just as well to point this out. Somewhere in here, instructions I have how to set up Kali. Okay. So in this mess, okay, SSH server. Service SSH start. Thought I did that. Oh, I put it in the wrong order. Okay, fine. Service. Service SSH start. Okay. Now let's see if I can finally connect to my machine and get us back on the track here. And we're in. Okay, so now we will resume, and it's just as well to demonstrate that because you will have the same problems. All right, and notice I didn't figure out what's wrong or fix anything. Just find different ways of turning it off and on again just to get through the day. Anyway, so let me get back to my slides. I just wanted to look at the memory with all those A's in it for CH2E. So it's GDB, CH2E. Okay, and now list the program. And now I want to put a breakpoint. This get S is the buffer overflow, and that's what I want to show you. Let's look at the memory at line 7. By breaking at line 7. Now if I run, and now I put in, say, hello, and press enter. Now it hits the breakpoint. Now I can examine the stack. Let's take a look here. You need to change the Kali root password. Of course I do, yes. Anyone on the LAN, anyone on campus could now hack into my machine. He's absolutely right, because I've now put it on the public network directly with the default password. So this is the sleazy stuff that people who don't care about security do, and that's the thing to know. Kali, by the way, is not secure against attack. It's an attack machine. You shouldn't be doing private things in Kali. It's intended to, you're the aggressor when you're using Kali. You're not defending yourself. Anyway, so now I'm in. I've got the breakpoint here. Now I can look at the memory with info registers, and I will see my stack goes from 5E0 to 608. So I can examine that with, say, 30X ESP. It's 5E0 to 608. So that is 600, 604, 608. That last highlighted thing is the 32-bit word starting at address 608. So that is the stored instruction pointer. And I typed in the word hello, and here it is in the first two words, HELLO. The L is for C, the O is for F. And if it's not easy for you to do ASCII in your head, it will be by the end of this class. But whenever you want it, just Google ASCII. And ASCIItable.net is right here, and you'll get used to reading this thing a lot. And what I typically, the easiest thing is just memorize 41 is A, and there it's just alphabetical. 42 is B, 43 is C. So I have capital H is 48, and a capital L is for C. So you'll be looking at characters in hex all through this class. So there are many ways to get an ASCII table, and you don't really have to memorize it, but you're going to have to memorize a few of them just to get through the day. So I can spot that the letters I typed in are up there, and the extended, the stack, the return address is over here. So I did not have a buffer overflow because what I put in fit in the space. Because you remember in the program, we reserved enough space for 30 characters. So let's run this program again and put in more. That's 10 A's. So I'm just going to copy that and put it in. So I put in 50 characters. Now it hit the breakpoint, and now if I do info registers, the stack is the same as before, 5E0 to 608, but I've used more of it. So if I examine the stack, which is this one, and I go down to 608, there. That is the stack frame. This is the stored instruction pointer. I have overwritten it with all 41s. This, by the way, the last highlighted value is the stored base pointer, and that's why you may remember we saw the base pointer was full of A's and the instruction pointer was full of A's. When it returns, it is going to be very messed up. It's going to think the base of the stack is here and the instruction pointer is there, and both of those addresses are illegal, so it will crash. But the point is we control those addresses. Those are just some of the A's we typed in. So we can take over the machine in principle. All right. And let's see, we've been here for an hour, and I've finished this part of it. Let me see if there's anything else worth mentioning here. I think it's about time. I just wanted to review. You have now learned 8 GDB commands, and that's really all you're going to need. There's a couple of fancy things we'll do with it later, but that's why GDB does not have to be baffling. There are 1,000 other things it can do, but who cares? These simple things are enough to get the job done. And that's good. We're down to the Cahoots, and I think we'll take a break before that happens. We're at 2:12. Let's pick up at 2:25. Give you a 10-minute break. So then I'm going to demonstrate the project and do the Cahoots. All right. And I'll pause the recording. The streaming will keep going for the people that are live, but I'll quit recording it so the people that view it later will not be as bored. Like I never turned it on for the whole second half, but that's life. Right. The recording. So the demonstration of the projects apparently did not get recorded, but.
Oh yeah, remember when you all gave me grief about taking pictures and recording in the class?
I didn't give you grief. Right. Anyway, this is so my recording. These amateur recordings I make are in many ways not as good. Yeah.
Do you have slides to do some of those project demonstrations?
I don't have slides, but I have complete instructions for you to follow. Yeah, yeah. So you don't really need my video, but I intended to make a video, but this tends to happen when I do it. Sometimes I follow it up. That's why the classes I get to do in the recording studio have better results, because there's a more professional human handling the recording.
Older copy of this
There is.
instantiation of the class that's posted on YouTube?
There is. Last semester has one, but you know, it was also done by me amateurly and might have similar defects. But anyway, yeah. So anyway, I'm gradually getting better at it, but it is a fact. It is not absolutely true that 100% of it gets correctly recorded. Yeah.
Train us where to look on the screen for what to see if it's recording correctly.
It's nothing you can see up there. You can, I know, but in fact, I only learned about pausing it from a student. I didn't know how to operate it. There's a, in fact, there should be a bar in my screen I'm not seeing. It says it's recording.
Well, you must have been recording because you got the messages.
Maybe I'm not streaming any. I'm not sharing my screen either. Oh, all right. Let me fix that. Somehow I'm not sharing my screen. Thank you for telling me.
Thank you.
That's
No,
what-
there's no screen. I'm wondering what the cahoots number is.
Yeah, that bar is supposed to be up there. Somehow it failed. All right. Anyway, thank you for reminding me about the cahoots. And if you do, send me a chat message if somehow you can't see the screen or something. I have various problems with this equipment, this amateur stuff. So I'll wait a few more minutes. So go to kahoot.it and put in that number, and you can earn extra credit if you get the most of these right. I'll get a piece of paper somewhere to write this on. Yeah, oh, that's right. There's also the grading policy I was supposed to have last week on paper. I now have it in case you wanted it. It's over there. It's not very exciting, but technically you can have one if you like it. It's legal compliance. All right. So
the crisis is over for the woman, previous professor, the people, right?
oh, I don't know, but
She had no body.
yeah, probably okay. Yeah, Elizabeth. Yeah. All right. So let's try these. There are 7 of these. All right. So what GDB command will show you the current stack frame? Okay. Okay. Examine some number in hexadecimal starting at the stack pointer. This number could be different, and if you put something other than X there, you'll see it in some other form like ASCII or something. All right, that's examine is what shows you the contents of memory. All right, what register has the bottom of the stack frame? Okay, EBP is the base of the current stack frame. The top of it is ESP. All right, so what is %X in that command? That is a format string specifying the format of how you're going to print it out, which looks harmless but isn't. All right. What GDB command will show you C source code? Okay, list. Okay. What memory section is the simplest to exploit? All right, stack is the easiest. All right. What register has the address of the next instruction? Okay, extended instruction pointer. All right, so what's the language that causes these buffer overflows? Okay, it's C, as we mentioned. It's like a car that's like a sports car. It's fast but dangerous. Anyway, so I got Amber Unix is going to have to tell me who they are to get points. Harvey, that might be a real name. And Peter D might be a real name. Anyway, all right. So those are the winners. Those people get 3 points. And if you, is Amber Unix in the room? Or online? Amber Unix? Aha, here comes a chat message. Might tell me who Amber Unix is. Any hints for Bourne shell white space? I'm not sure. Space tab new line? I'm not sure. It's a good question. I'll have to Google it. All right. And a new message says, and not in your classes. Oh, Amber Unix. Okay, fine. So Amber Unix, you don't get the points. It doesn't matter. Good. All right. Or I'll just record it under that name. Okay, that's fine. Not in class. All right. I'm going to turn off the share now. Have a good night, folks. See you in a week. All right. End meeting. End meeting.